Good evening, students. Today we are going to see transistors. So generally, transistors plays a very vital role in our day-to-day life. Mainly, the transistors are used in our mobile phones, TV, and in addition to this, microchips, integrated circuits. So many applications we have in our day-to-day life. Today's class, we are going to see about what about the transistors manufacturing, or what are the raw materials can be used to make this transistor, and what about the configuration of transistors, okay, and in addition to this, what are the types of the transistors, likewise we can see. Now, as we discussed, transistors are nothing but the building blocks of integrated circuits and microchips, and they are basically used as they are basically used as electronic switches or amplifiers. Okay, so they are basically used as electronic switches or amplifiers. So due to that reason, they can be used to control they can be used to control the flow of electric signals. Okay, here they can be used as to control the flow of electric signals. Clear? Next, we will see about what are the parts of the transistor. Okay. Next one is parts of a transistor. So if you see, it consists of three parts. One is nothing but the emitter, another one is the base, and third one is the collector. So emitter, base, collector are the three main parts of a transistor. And if you see here, they are made up of the semiconducting materials. So here we know the best examples of the semiconductors are silicon. Okay, silicon or other semiconducting materials can be used to make this transistors. Okay, so what are all the raw materials here we can able to understand. And if you see what is the main property of this semiconductor, so if you add the impurities, or if you increase the temperature, they can either conduct or block the electricity. Okay. So due to this reason, they can be perfectly used to make the transistors. Okay. So from this we can able to understand what are all the raw materials to make the transistor and what are the three main parts of the transistor. So it consists of three main parts. They are nothing but the emitter, base, and the collector. So here you can able to see the symbol which is being used to represent the transistor. Here you see this is the base, collector, and the emitter. And in the case of emitter, we have placed one arrowhead which is being pointed outside. And in the forthcoming slides, I will explain why this is being pointing in the outward direction. Okay. Then we will see about the main functions of the three layers, the three parts of the transistor. So here emitter, first one is emitter, and it is the top layer, and it is acting as the source of electrons. Okay, and it is also a heavily doped region. Okay, heavily doped region. Next one is the base. Base. It is the middle layer of the transistor, and it acts as the control terminal. Okay, it acts as the control terminal, and it is lightly doped, and it is lightly doped, and it is used to regulate the flow of electrons from the emitter to the collector. Okay, so next one is the third layer. Third is nothing but our collector. So top layer is completed, middle layer is also completed. Then third one is our bottom layer. Bottom layer, it acts as the drain. Okay, so which means collecting electrons and sent from the emitter. It is the drain terminal, and it sends the electrons out. Okay, and it is moderately doped. Okay, moderately moderately doped region. Okay, so these are all the three main regions: emitter, base, collector. And we have discussed what about the doping level of these three regions of our transistor. Okay, next we will see what is a transistor and its function. So transistor is a fundamental semiconductor device used to amplify or the switch the electrical signals and the power. Simply we can came to know the transistor can be used as an amplifier, or it can be used as a switching device. Okay. So in this case, if you see when a small current, if it is applied to the transistor base, say for example, I will show you the diagram. Here, this is collector, and this is our emitter, and this is our base. So base, collector, emitter. If a small current, if it is being applied to the transistor base, okay, if I am applying the current to the base, it allows a very large current to flow between the collector and the emitter. Okay, and due to this, what will happen? So the base, which controls a much flow of electric current. Okay, so it became able to understand it is going to act as a valve. Okay, so it is going to be act as a valve, which means a very small pressure or a little pressure is being applied on the base terminal of a transistor, and it much controls the flow of electric current between these two, the emitter and the collector terminals. Okay, And the next case, if there is no current, okay, if there is no current is being applied to the base of the transistor, what will happen? The transistor will be acting as a closed switch. Okay, it will be acting as a closed switch when there is no current given to the base terminal of the transistor. So from this, we can able to understand it is going to act as a switching device. Okay, and the next one is here. If you see, they given the second point as a switch. The transistor can rapidly turn on and off, representing the binary states of 0 and 1 that form the foundation for the digital computing. So, from this, we can able to understand that transistors can be used to make the digital computing processes. Okay, so as a switch. Then come to the third one here. As an amplifier, transistor can also be used to boost the weak electrical signals. Okay, so in this case, a small input signal is applied to the base. Again, we are going to give a very weak signal. Okay, very small or a weak signal which is being given to the base, and can control the very larger signal between the collector and the emitter. Okay, and it can amplify it. So this type of processing, which means the amplification, very small signal, it is being amplified. This can be used in the case of our radios, televisions, audio systems, etc. Okay, so which can be used as the switching device in the case of digital computing, and secondly, amplifying process can be used in the case of radios, televisions, audio systems, etc. So here we can get a clear idea about what is a transistor and its functions. What are the types of transistors? First one is bipolar junction transistor. Second one, by unipolar junction transistor, field effect transistor, junction field effect transistor, metal oxide semiconductor field effect transistor, insulated gate bipolar transistor, avalanche transistor, stocky transistor, diffusion transistor. So these are all the various types of transistors we can able to use. Okay. So in today we will see about this the bipolar junction transistor, which can be represented as BJT. Okay. So next is the bipolar junction transistor, BJT. Bipolar junction transistor, it is a commonly used transistor. Again, it consists of the three parts, that is nothing but our emitter, base and the collector. It can act as a regulator for both the electrons as well as holes, okay, which can be used as a regulator for electrons as well as holes, okay, electrons as well as the holes. And here, if you see, the BJT can be classified into two types. They are NPN and the PNP transistor. So very simply, we can able to construct this PNP transistor and NPN transistor with the help of the P-type and N-type semiconductors. As you know that P-type and N-type can be prepared with the help of the adding impurities of pentavalent and the trivalent materials. So here, if you see the case of NPN transistor, first I am going to take P and N junction. This side, if you add N, I can able to make the NPN transistor. So this will act as a NPN transistor. And next one is PNP transistor. For this also, I am going to take the same P and N junction, and the next side I am going to add the P. So it will act as the PNP transistor. Okay, so here this is the symbolic representation. In this case, NPN transistor, this is our emitter, this is base, next one is collector. Similarly, this side here we have this is collector, this is emitter, and this is base. As you know that the transistors can be easily represented by means of this arrowhead. Okay, so wherever we are putting the arrowhead, which represents the emitter junction, emitter terminal, and here, especially in the case of NPN transistor, the arrowhead is pointing outward. And whereas in the case of PNP, the arrowhead is pointing inward. Next, what is a transistor configuration? Okay, so here if you see the diagram, we have three basic configurations. One is nothing but common base configuration. Second one is of common emitter configuration. Third one is of common collector configuration. So totally there are three configurations are possible in the case of transistor. Before that, you should know about what is meant by the configuration in the case of the bipolar junction transistor. It is nothing but the different way of connecting the transistors, different way of is of connecting transistor in electric circuits to perform specific functions. Okay, so simply we can able to understand the configuration which represents the different way of connecting the transistor in the case of different electronic circuits to perform different specific functions. Okay, and accordingly it consists of the three basic terminals. One is nothing but the emitter, base, and another one is of collector. And in the first case, if you see the common emitter connection, common base configuration, in this case the base is the common terminal, whereas the input is applied between emitter and the base, whereas output is being taken between collector and the base. Secondly, in the case of our common emitter configuration, emitter is connected as the common one, and in between this emitter and the base we are going to give the input, and in between the collector and the emitter we are going to take the output. Okay, next one is the common collector configuration. So in the case of common collector configuration, this collector is given as the common terminal, and input is given between this base and the collector, whereas output is taken between emitter and the collector. Okay, so here these are all the three basic configurations, and next we will see what is the use of these configuration. Here the configurations are mainly used to determine the behavior, used to determine the behavior of different characteristics, different characteristics, amplification properties, amplification properties of a transistor. Okay, so here if you see the common base, common emitter, and the common collector configuration, and especially this common base CB configuration, common base CB configuration can be used to get the high gain or high voltage gain So this common base can be used to get high voltage gain, low input impedance, and no current gain. Okay, so from this CB we can able to get these characteristics: high voltage gain, low input impedance, and no current gain. And the next one is our common emitter. Common emitter. In the case of this common emitter, we can able to get high voltage, and current gain, high voltage and current gain, and they are mostly used in the case of in amplification process. In amplification process. And the next one, third is nothing but our CC, that is common collector configuration. So in the case of this common collector, high input impedance, low output impedance, unity voltage gain, and which can be used to make are used for impedance matching. Okay, or you can here also we can add used in the case of high frequency applications. Okay, so the configurations based on that we can able to use it for different applications. Okay. Okay. Next we will see about operating regions of a transistor. So there are basically four regions. One is of active region, second one is of saturation region, third one is of cut-off region, and inverted region. These are all the four basic operating regions of transistors. Now we will see one by one. Here you can able to see the active region diagram. In the case of active region, here the emitter base junction is forward biased. Okay, so this is our emitter and this is our base and this is our collector, and especially this is nothing but our NPN transistor. Okay, NPN transistor. In this case, the arrowhead is pointing outward, so we can able to understand NPN transistor, and emitter and the base is nothing but our forward biased, and in addition to this the collector and the base is reverse biased. Here this is forward biased and this is reverse bias. This is reverse bias. And the voltage VEB is connected between the emitter and the base in the case of a forward manner, whereas this voltage VCB is connected between the collector and the base in a reverse manner. And in this case, the active region, it can be mainly used for amplification. Okay, and in addition to this, the collector current depends upon base current. Okay, depends upon base current. This is the information regarding about our active region. Next, Here is our saturation region diagram. This is the saturation region diagram. Here also we are considering the same NPN transistor. In this case, it is this emitter base is the forward biased, and the collector base junction is also forward biased, forward biased. And this VBE is connected between emitter and the base in a forward biased manner, and the voltage VCB is connected in between this collector and the base in a forward biased manner. Okay, and here in the case of the saturation mode, which can be used, or we can say the transistor is in the saturation region. It can act like a closed switch. Okay, it can be act as a closed switch. Next, we will see about the third region. Third region is nothing but our cutoff region. In the case of cutoff region, in between this emitter and the base, VEB is connected. Here the emitter and the base junction is reverse biased. It is reverse biased. And the collector and the base, it is also reverse biased. Okay. And here in this case, the value of current in the transistor is nearly zero. Value of current, value of current in the transistor is nearly zero under this cutoff region, and the emitter won't or does not, we can say the emitter does not emit any charge carriers, any charge carriers to the base, except few minority carriers. Okay, and this carriers is also mainly due to the thermally generated charge carriers only. So we can say under this region, this acts like a open switch. Next one is our inverted region. In the case of inverted region, emitter base junction is reverse biased, whereas the collector base is under forward biased. Okay, in this region, the transistor does not, we can say, under this inverted region, the transistor does not work properly. Does not work properly. So this region we can able to say this is not much important region. We are not going to bother about much regarding this inverted region. Okay. So basically the three regions we have discussed: active, saturation, and the next one is nothing but a cutoff region. So these are all the basic three regions we have to consider for amplification and the switching device. Okay. Next, we will see how does a transistor work. As you know that transistors consist of three main regions. One is nothing but the emitter, base, and the collector. Okay. So here, with the help of the base, how it is going to act as the switching device, we are going to see. Before that, you see, when a small electric current is applied to the transistor base, it allows a larger current to flow through it, which means between the collector and the emitter. Okay. So based on the uh, current given to the base of the transistor, we are going to get the output in between the collector and the emitter. So here if you see there is no current at the base, the transistor acts like a closed switch. Okay. So no current flows between the collector and the emitter. Secondly, if there is a current at the base, the transistor opens up. So from this we can able to access this current in between the collector and the emitter. Okay. Okay. So this is where the transistor works. Based on the amount of electric current given to the base of the transistor, we are going to make the transistor to behave as a switching device. Next, we will see the operating regions of a bipolar junction transistor. Here you can able to see the three main regions, and before that if you see the first one is the saturation region. Already we have discussed in the previous slides also. Saturation region. Second one is nothing but our active region. Third one is the cutoff region. Okay. So these are all the three main uh, regions, that is operating regions of a bipolar junction transistor. As you can able to see, we are going to take this current along the y-axis and the given voltage along the x-axis. And how beautifully for the given voltage the current lies. It is clearly given in this picture. And we have three separate regions which is denoted with the help of the different colors also. As you know that the saturation region, it is given here, saturation region, and they have given this as the transistor is fully on. That means in the on state. And the next one below here it is highlighted like this. This is nothing but the cutoff region. Here the transistor is fully off. Okay, the saturation region indicates the on state of the transistor, whereas this cutoff region indicates the transistor is in the off state. And the remaining is nothing but our active region, which is given as the Q point. Here, the transistor is somewhere between the on state and the off state. Okay, somewhere in the on state or off state. Okay, so this active region indicates the in between state of a transistor. Okay, so if you want to use the transistor as a switch, you have to make the transistor to change in between this cutoff as well as the saturation region. So the transistor, if you want to make or include in certain circuits, it must be maintained in between the saturation region and the cutoff region. So this is nothing but our operating regions of a bipolar junction transistor. Next, here the next heading is NPN transistor as a switch. Okay. So suppose if you want to make a 24-watt bulb is going to grow. For that, you are having the input signal as the 0 to 5 volts. And in terms of digital, if you consider it is in terms of 0 and 1. Okay. So in that case, you cannot able to apply this digital signal 0 and 1 directly, and by using this transistor, so it can be of NPN or it can be of PNP, you can make it as a switching device. With the help of this, the input signal can be given and the lamp will make to glow. Okay. So very simple circuit. How we are going to use it as a switch. Okay. With the help of this a small example, we can able to understand. And here, if you see, here I have given this, the input signal is set as 5 volt. Okay. So input signal as 5 volt and the current flows, current which flows through this RB. Okay. Current flows through this RB, which causes the transistor to act as a switch, which means turn on the lamp, turn on the lamp. So here very easily we can able to understand this working of a transistor as a switch. The digital signal is denoted here, uh, just varying of this 0 and 1, and whereas this 1 given as the input, which means 5 volt, here you are giving, and this current which flows through this RB, which means the current is given to the base of the transistor, and we can able to get the output in between the collector and the emitter. Already we have know the how transistor works, in that we have discussed. So in this way, a transistor can be made to behave as a switching device. Okay. So when the digital signal is 0, no voltage is applied, and consequently there is no current flows through the transistor, which means there is no current flows through RB, and due to that the transistor is acting as an open switch, or if the digital signal is 1, it acts as a closing switch. Okay. Next we will see why is the transistor works as an amplifier. Okay. So transistor, as you know that it already act as a switching device. Now we are going to talk about the amplifier. So here a transistor strengthens a weak signal by acting as an amplifier. And the emitter base junction, if you take this is nothing but the NPN transistor, and we are going to take this, the emitter base junction, emitter base junction. Here we are going to take it as input region, and in the input junction is being kept as the forward biased, as a forward biased, whereas here collector base output is being reverse biased, okay. And here if you see the signals polarity, so without any changing, here the no bearing on the preservation on this forward bias, and an amplified coupled transistor which is being given in the diagram. And here before entering into this main working as an amplifier, we should know about certain definitions. So what are the definitions? First one is nothing but our input resistance. And you know about this IE represents the emitter current. This is IC collector current. Here we have the IB as the base current, and here we have emitter base voltage, collector base voltage, load resistance, input signal. So these are all the explanations for the symbol being used. And as I told, the definitions are nothing but, first one is nothing but RI. What is RI? Input resistance. Input resistance. So here, with the help of this formula, we can easily able to give the definition. Input resistance R is equal to ratio between VEB to IB. IB. Okay. So it is the ratio between, the definition is, it is defined as the ratio of the negligible, very small change in the base emitter voltage to the base current. Base emitter voltage to the base current. So this is the first definition. Okay. So the input resistance is defined as a small negligible change in the emitter base voltage to the base current. And secondly, we are going to talk about RO. RO is nothing but our output resistance. Output resistance. Output resistance. RO, which is equal to del VCE to del IC. So it is defined as small change in the collector emitter voltage to the small change in the collector current, to the small change in the collector current. This is our second definition. And then we are going to talk about the effective collector load. Effective collector load. The name suggests, as the name suggests, it is nothing but the load, LOAD, load linked to transistors collector. Okay, so that is called as effective collector load. If you take a single stage amplifier, okay, if the transistor, if it is acting as a single stage amplifier, the output voltage taken from the output voltage can be obtained from the transistor's collector. Suppose if it is of multi-stage, we have to go to the cascaded stages. Transistor, it is being connected in the cascaded stages. So it is, by the definition, the entire effective load is nothing but the can be given in terms of the formula RAC, which is equal to RC parallel to RO. So in this case, if you see what is RAC, RAC is equal to RC into RO divided by RC plus RO. Okay. So the effective collector load for a single stage amplifier is RC plus RO, RC plus RO combined in parallel. RC plus RO combined in parallel. Okay. So this is the third definition we should keep in mind. For a single stage for amplifier, hence for a single stage amplifier, effective load is equivalent to the collector load. Okay. Effective load is equivalent to the collector load. Next one is the collector gain, sorry, current gain, voltage gain, and the power gain. So here, if you see these three definitions, next we will see. Next, as I told you, the current gain. CURRENT, current gain. Okay. So current gain. Current gain is nothing but the gain in terms of current that which is being noticed when the changes in the input and the output currents occurs. Okay. So current gain is nothing but the changes being occurred in the case of input and the output currents. Okay. Changes occurred in input and output currents. Okay. So this is called the current gain. Here, next we will see about the voltage gain. So voltage gain is nothing but the for the given input voltage, for the given input, for the given input, what about the amount of voltage gained? Okay, or we can say if there is very small variations in the input and the output currents, what about the output voltage? Okay, and the third one is nothing but the power gain. So the power gain is being absorbed in the power output signal. When the input signal is passed through the amplifier is called the power gain. And here I will write the gain absorbed in power output signal when input signal passed through the amplifier. This is called as the power gain. So we will write the formula one by one, most related only. So here first one is nothing but our current gain. So current gain is usually denoted by the letter beta. Okay, current gain is denoted by the letter beta, which is equivalent to this del IC to del IB. Okay, and that means the small change in the collector current to the small change in the base current. Next one is voltage gain. So voltage gain is nothing but the amount of voltage gained when the variations in the input and the output currents are noticed. So here if you write this which is denoted by AV, here delta VCE by delta VBE. Okay. So very small change in the collector emitter voltage to the collector emitter voltage to the base emitter voltage. Okay, that is the voltage gain, current gain and voltage gain we finished. What about the last one? Last one is nothing but the power gain. So power gain is simply we are going to give it as AP. So AP which is equal to beta into AV. After writing this, you all know the product of this current gain and the voltage gain is equal to the power gain. Okay, current gain and the voltage gain which is equal to the power gain. So these are all the basic definitions we should know before entering into the as an amplifier. Okay, so here we have given the transistor as an amplifier working characteristics curve. So this curve is being divided into three equal parts. One is nothing but the cutoff region, saturation region and the active region. As we completed earlier, this cutoff region and the saturation region, which is going to act the switch, as the switch. So here also it is going to act as a switch. Okay, so the very little signal, input signal is given to the base emitter junction. Then what about the output? In this way, it is going to act as an amplifier. So the amount of amplification that a transistor can provide, which can be determined by the which is determined by the current which is given to the base. Okay, as we discussed in the previous cases. So based on the input given, it is going to act as the amplified signal, or it is going to act as a amplifier. And in this curve, actually if you come to this case, in the case of active region, so we have to more depend on this active region, because in this region only it is going to act as an amplifier. Okay, so in the active region, transistor acts as an amplifier. In the cutoff region and the saturation region, it is going to act as a switching device. Okay, and next one is we have to concentrate on the slope. Okay, slope of the curve. In the slope of the curve, we are going to see this voltage gain. Okay, so what is voltage gain? Voltage gain is nothing but the AV represents the voltage gain. It is nothing but the ratio of the VCE to the VBE. Ratio of VCE to the VBE. That means output voltage to the input voltage. So, based on this active region, we can easily calculate how much signal is being amplified. Okay. So, this is regarding about this characteristics curve. Okay. Next, transistor as an amplifier circuit diagram. Okay, and the same NPN transistor we are taking. In addition to this, we have added capacitors. Okay, so input signal, output signal is shown in the diagram. So in the transistor as an amplifier circuit, usually we are going to use the common emitter configuration. Okay, common emitter configuration is usually used for the transistor as an amplifier circuit. Okay, so the first half of the BJT means here we have emitter base. Okay, emitter and the base is being forward biased, is forward biased. Collector emitter is reverse bias. Collector emitter is reverse bias. So in the circuit diagram given is nothing but the common emitter configuration and the input signal. Here we can next we will see about this input signal and the output signal. So in the case of input signal is out of phase. Okay, so input signal is out of phase with output signal, and especially from the diagram you will be able to see 180-degree phase difference. 180-degree phase difference. Okay, And the next thing is capacitors. So capacitors we have added in the circuit. So what is the need of the capacitors being here? So the capacitors are used in the circuit to block the DC, that is direct current, and as well as to give the input signal as AC, that is alternating current only. Okay. So capacitors are used to block Capacitors are used to block the DC. I'll write it as DC, direct current from the circuit, and only pass, only pass alternating current, only pass alternating current. Okay. So what is the need of the capacitors being included in the circuit? It is used to avoid or used to block the direct current and to allow the alternating current. And I'll write the equation, that is current equation of a transistor. So here IE, which is equal to sum of IB plus IC, which is IE is nothing but the emitter current 2, which is equal to the base current plus collector current, collector current. Okay. So this is regarding this circuit diagram here. Here we will talk about the signal, how it is being amplified in the next slide. Okay. Next, we will see the common emitter transistor as amplifier. So, for any small signal, if it is being amplified, so the maximize the input signal amplification while minimizing the distortion. Okay, to the output signal. So, if you want to say in the other words, so if you hear the output signal should be an identical replica of the input signal, although it is being magnified. So I'll write this here. Output signal, output signal should be an identical replica of the input signal, although magnified. Okay. So this is nothing but the amplifier. When it is being used or utilized as an amplifier, the operational Q point, which means Q point. So if you are using this as amplifier, first we should know about the Q point. What is Q point? It is nothing but QUIESCENT, quotient point. Quotient point must be chosen, must be, or you can give it as must be properly chosen. So first thing is we have to identify the Q point. Okay. Why we have to choose this Q point? To get the minimal distortion, minimal distortion. So this is actually the amplifier's DC operating point. What is this Q point? It is nothing but the amplifier's DC operating point. So, and with the right biasing configuration, you can easily determine the position at where the load line, at the case of load line, we can easily able to identify the Q point. So this is the thing we have to keep in mind while operating the transistor as an amplifier. So in order to provide a class A type amplifier, or in the case of operation, the ideal location for a Q point is very close to the load line. Okay. So if you are using the transistor as an amplifier and the two class A type, this Q point is very close to load line, center, okay, load lines center, okay. And next one is if how it is being acting as an amplifier. So once the Q point is fixed, okay, once if the Q point is fixed through the DC biasing, then the AC signal is applied at the input. As we know that we are going to filter the DC, whereas we are going to only give the AC. So once if the Q point is fixed through the DC bias, then the AC signal is applied as an input using the amplifiers. Okay, so which can be called as the coupling amplifiers, sorry, coupling capacitors. Okay, so the AC signal is given as input using coupling capacitors. Coupling capacitors, that is C1. Here I will write, that is C1. So during this positive half cycle of the signal, okay, during the first half cycle. So here I will write during the first half cycle of the input signal. Then here this VB, the signal VBE increases leading to the current. Okay, so I'll write here. Here half cycle of the signal, half CYCL cycle of the signal to VBE base emitter junction increases which one? It is IB. Okay, base current is increases, and as a result of this IC increases. So because of this IC, collector current increases, and there is a limit how much this collector current should be increased. So it is beta times. Okay, it is beta times. What is the beta? Beta in the previous slide we used, isn't it? So what is beta? Beta is nothing but the collector current, sorry, current gain. Okay, so here beta times the collector current increased by beta times, leading to decrease in the output voltage. That is here we see E. Okay, so thus this common emitter amplifier, okay, common emitter amplifier produces an amplified voltage or amplified output. Okay, so it gives a amplified output with a phase reversal. Okay, so these cases during the first half of the signal, this VBE, then the help of this increases IB, so it increases this IC, and how much times? It is of beta times. So here it leads to the amplified output with the phase reversal. So the output gain of this common emitter amplifier is equal to the ratio of change in the output voltage to the change in the input voltage, change in the input voltage. So here already you know the voltage gain formula. Voltage gain formula is nothing but the delta VCE to delta V delta VBE. Okay, so in this way a transistor can be used as an amplifier. Here we have the characteristics of common emitter amplifier curve. Again, active region. In the active region, it is going to act as an amplifier. and saturation region also here, breakdown region is also here. So with the help of this characteristics curve for various voltages with IB as constant, and here this IC we can able to get the output. Okay. Next one is, what about the advantages of transistor if it is being used as an amplifier? That is, it possesses a very low input impedance and inverting common emitter amplifier. And in addition to this, high in output impedance, high voltage gain, high current gain. So these makes this transistor as advantage one if it is used as an amplifier. Okay. So next one is disadvantages. It has a high output resistance. It responds poorly to a very high frequencies. It has high thermal instabilities, and its voltage gain is very unstable. So this makes transistor as a disadvantage if it is act as a amplifier. And where we are going to use this transistor, especially common emitter transistor as amplifier means in the case of radio signals. For radio amplification, radio signal amplification, we are specifically using this common emitter as a common emitter transistor as an amplifier. And in the wireless communication we are using, and in addition to increase the strength of the signal, we are using the transistor as an amplifier. So these are all the uses of transistor is being used as an amplifier. So finally we'll conclude here. If we apply the input signal of 0 degree phase, then output will be observed to the phase difference of 180 degree. Okay, so the common emitter amplifier design is called the inverting amplifier. Okay, so this is the conclusion we should keep in mind. Thank you all.